Chalo, let us will start. Others will join. Once they will finish the practical, they will join the lectures. Okay. So last lecture, last lecture we have seen about the CCP model in the peak controller, and that CCP defines its capture, compare, and the PWM generation. So out of that, we have done with the first model that is called as a capture. Okay, so any transition going on in the clock cycle can be captured by storing that value in the CCP align the CCPH registers. So that 16-bit value can be captured from the timer values that we have seen from that block diagram. Okay, and how that values can be controlled, can be assigned. It depends upon the this control register that is called CCP1 con or CCP2 con control registers. The same format will be there for the CCP con and the CCP2 con. So again, I'm repeating this part because this bit is for again compare mode and the PWM mode generation. So from in CCP1 con from the M0 bit to the M3, that will decide the at what value I want to capture the data, either at the rising edge or falling edge. The same time, which value it will be captured, that will define from the these 4 bits. Okay, and after the 111100 that bits, and along with the bit number 4 and the 5, that is CCP XX and the CCP YY. So this CCP XX and the CCP YY hold the duty cycle values. That is used in the PWM generation. Okay, so out of that, now we'll see for the CCP con registers for the comparison, that is compare mode. Okay, so this thing we discussed yesterday only for lecture, that is for capture. So based on that CCP M0 to M3 bits, if these bits will be like this 0100, what will be captured means that module CCP model operate in the capture mode, and at rising or falling edge the data can be captured. It depends upon these format bits. Okay, now once the value will be from that 3 zeros to the 1010, that time it operates in the compare mode. So simply what happens in the compare mode, it has the compare registers, 16-bit compare register. So by using that compare register, the value stored in the timer can be compared with the help of the timer to value registers. Okay, so again in the comparison mode, we have the comparator, simple meaning. This is my comparator. Okay, so one value is giving comparator from the CCP 1L, I can say IH, and CCP 1EL. So it will hold the 8-bit values of each total 16-bit comparison value. Okay, so value to be loaded, what value will be compared, that can be loaded in the these registers. For example, it will hold the 1.8, last is told, and this will be 4B. The same value I am comparing, okay, from the, so which timer provides the timer capture and compare? Timer 1 and timer 2 for the PWM generation. So I have the timer 1H. It's not TR, TMR1 H, and the TMR1L. It holds the 16-bit values, okay, to value to be captured. So once the value will be started, the timer 1 start raising the value to 16-bit register, we know it. Okay, so 216 that will count. So count starts increasing. Once the count value will come at this value of 4B18, what happens? Exactly match occurs. And once the match occurs, that control needs to take the action. Means the interrupt can be generated for the CCP1IF flag. This flag will be set. Means this operates in the compare mode. This is operation we are looking for in the comparison mode. Okay, let's go with the diagram. So but thing is what? We need to control the CCP value, CCP with the bits, that is 4 bits M0 to M3. Okay. The same as I mentioned, the depends upon the state bits for the control register M0 to M3. So bits from 1000 that can for remaining bits will be used for 1000 to the 1010. That bits will be used for the compare mode operation. Okay, and we're setting the value of that compare in the register, and that value compared in the timer one register values. And once a match occurs, the flag will be raised at the pin RC to CCP1. Okay, so this is the block diagram for that. Let's understand that values. Okay, see, this is the value CCP or CCP R1 H register, CCP1 RL. So it will hold the lower 8 bits. This will hold the upper 8 bits. So what is the value I'm storing? This value continuously comparing with the values coming in the timer 1 registers, which is a 16 bit. So once timer will be start, the count value of it will be increases. As this value increases at certain value, this value and this value will be exactly matching. So once match occurs, we need to take the action. That is the CCP1 flag will be set. The same time, okay, I'm making that RC2, that CCP1 pin as output. And that time, once this pin will be high, based on the logic operation, the CCP1 bits are given. That will be set or reset the this flip flop, and I'm getting as a output signal at this moment. This is simple operation for the compare mode by using the peak controller. Next, as I said that CCP, the third is going to be Pwm mode operation. Okay, so in the Pwm means what happens? The pulse width of the that signal varies. Okay, and based on this Pwm variation, so this mostly in the speed control of the DC motors in the conveyor belt systems or industrial applications. So how this Pwm waveform can be generated with the help of this model, we have to look here. Okay, so again I'm defining here what CCP1 con registers. In that, once these 4 bits data is going from 11111. So I'll copy these bits and I'll put in the paint here, so I'll understand that. So in this register, once this value is going from upper value is 11 bits, and these bits doesn't matter. We can take any bits. Okay, so from starting 000, these bits to the 0111, it can operate in the capture mode. Okay, from 10000 to 1010, it can operate for the compare mode, because same register is for the 3 modules: capture, compare, and the PWM. And PWM from 11xx. This value can be anything. 1x00 to the 4 times 1. Okay. The same time, once we'll configure these bits will be 11. This that CCP model operates in the PWM operation. So what happens in the PWM operation? We need to vary the this T on period. So it may be 50%, it may be 60%, it can be a 90%, like this. So this PWM generation can be varied by putting the value of the duty cycle here. And what is the duty cycle? We have seen yesterday only. So duty cycle is defined as T on period divided by T on plus T off. So when you talk about one clock pulse, it has the T on period and the T off period. So this T on period we have to calculate by using that formula is there for calculating this T on period. And this T on period always I am loading in the PR2 register to operate in the PWM. Okay, so when this value is loaded in the PR registers in that PWM generation, this value is going to compare with the timer 2 register value. And by comparing this, the signal will be set by flip-flop. Once this value is over, same value I'm comparing in the CCP1 L register, L and H register. Same value. Means once this PR2 value is going to be over, it goes low and provide the low timing interval, what remaining time interval. So like this, I can configure this CCP model for generation of the pulse width modulation technique. And how to do, I define here. First thing is what? In the CCP con, I need to configure this upper higher M2 and M3 bits as a 1 1, and M0 M1 you can take any values. So based on that, it can operate in the PWM mode. The same time, the 4 number bit and the 5 number bit, I need to put the duty cycle, what is duty cycle required. It may be 50%, it may be the 60%, like that. So based on this 50% duty cycle, I need to find the T on period. And this T on period, I'm loading in the PR2 register. Once loaded, we have this operation of the block diagram. Let us see that. Before that, I'll show it your how that. Let us see here. I have connected LED, and by varying the duty cycle 25, 50, how that on period going to be increases, you can just see here. You'll understand that. Means when I'm getting the higher duty cycle, the LED glowing is for the maximum time. So you can replace this LED by motor. So the motor will be rotated for the long time interval. So simply the duty cycle defines how much time certain action can be taken based on the T on period. And we need to configure PWM for the T on period. Okay, so T on can be changed as per the we are designing for that. So let us see that how to configure PWM model. Okay, so here is the diagram for that operation of the PWM. But the first thing, we need to set PWM period. What is PWM period? Means duty cycle. What duty cycle I require, I can put in the PR2 registers. So I'm putting in the PR2 register. And this PR2 I'm storing at these 2 bits, 5 and the 4 bit. These 2 bits can hold the duty cycle of the PWM output. Okay, so once I store this value, start comparing the, I need to make the timer on. Okay, the same time, I'm copying the duty cycle, the make CCP1 pin output. That time, same time, I need to make this signal as a output pin. The same time, I'm loading the duty cycle values in the CCP1, CCPR1 register, that is lower byte and the higher byte. Okay, so set the PWM duty cycle by writing the CCPR1L registers in the CCP con 54 bit, as I said here, these bits. So same time I'm copying in this value and I'm making the timer on. Once timer is making on, what happens? The value of timer starts comparing with the this value. Okay, means unless this will not match, what happens? The signal will be go low. Once match occurs, it will set the RS flip flop. Set means what? I'm getting the high pulse here. How much time? Unless what is the T on period I am mentioning here will not be matched. And when it will match, what is value stored in the duty cycle in this register? Once match occurs, it will reset the flip flop and the signal goes low. So like this, I am getting the variable PWM output at this RCP P1 pin by configuring this. How to configure this I mentioned. I'll repeat the point. Okay, what is the time installed? For example, if I want the 5 kHz signal, based on the 5 kHz signal, what is the T on period? I need to load in the this register PR2. And what should be the duty cycle? I need to copy in the this register and just make the timer on. Once I made the timer to on, what happens? The value stored in this about time interval PR2 registers comparing with the timer 2. Okay, unless it will not matches, the comparison will be signal will goes to the S pin. When exactly matches, what happens? This time value on this will set the flip flop and I'm getting the high level output. How much time high level output? Unless the comparator above comparator output will not be getting the high. If it will high, same value at timer 2 I'm comparing with the duty cycle what is mentioned in the CCP1L registers. Once this value matches, it resets, means signal goes low. Okay, so like this I'm getting the signal high and the low. High value based on the PR2 value stored up to that. And when it goes low, what is the value stored in the CCP1L registers? Okay, so like this I can configure the PWM generation output for the variable duty cycle. So one example I taken here, I'll show it. Just understand how to find the PWM time period. Okay, So PWM period is equal to that value I need to put in the that CCP XX and the CCP YY. That value can be stored like this in the PR2 register. How to find? Let's see, understand. So PWM period is equal to formula PR2 values to be stored plus 1 into 4 into what is the crystal oscillator frequency, timing interval of that. Okay, T oscillator means time of the oscillator into timer to prescaler value. So as we know, the timer 2 has the 16-bit timer, 8-bit timer, but it has the 16-bit values of that post-scalar as well as the prescalar. That value should be multiplied here. So example taken, suppose crystal oscillator frequency is 20 megahertz and output of the PWM I need of 5 kilohertz. Okay, so based on this two condition, I can configure the PWM output. How? See, PWM period is equal to 1 upon frequency, that is the T is equal to of that. 5 kilohertz signal is there, means I can find the PWM period, T on plus T off. The total gives the 5 kilohertz. So in the 5 kilohertz, I don't know what is the T on, T off, but I can configure that. Okay. So is equal to 1 upon frequency, that will give 1 by 5 kilohertz is equal to 0.002 second. That is the timing instant. So that timing instant, based on that value of PWM period, I am putting here, and I can find out the what should be value in the PR2. So that 0.002 is equal to PR2 plus 1. I know the crystal frequency 1 upon 25 kilohertz into 16. That is the prescalar value multiplies. If you solve this, I'm getting the PR2 plus 1 is equal to 250. So that PR2 is equal to 249 in the decimal. So if it compare this value in the hexadecimal, that will becomes F9. So this PR2 F9 value I am loading in the PR2 register. Okay, and I'm starting the timer. But timer counter at this certain level, this timer to value will be exactly coming at the F9, and the match occurs. That time it will be set the flip flop. Okay, if this value changing, I'm getting the different duty cycle. So I can configure like this. So based on the MCQ can be asked like this. For the frequency of 5 kilohertz, what should be the value to be loaded in the PR2 register, or what is the duty cycle I'm getting? So we need to do the calculation like this. Just from the frequency given, find the T out time interval, that is the time period. So based on the time period, just put the values in that and find the PR2 value. That was in the hexadecimal, not in the decimal. So here is I define various duty cycles, 25% how it looks like, 50% like this, 75% like this. And I shown here also in that animation slide, the duty cycle changes and what action happens here. So this LED will be glow for the long time interval if the duty cycle is going to be maximum. I want to start this CCP model. In that both three models are there, capture, compare, and the PWM generation. Collega Sarvanna. Then we'll go with the next point. Have you understood this? Mahesh?
Yes, sir.
Okay. And here is the sample taken. If the frequencies, I'm getting various frequency, variable frequency for the PWM. The what should be value should be multiplied as a prescalar in the timer 2, and what should be value to be uploaded in the PR2. Means by doing the calculation, some table is mentioned here, sample value. If the frequency I need PWM output of 1.22 kilohertz, the PR2 value will be FF, and prescalar will be 16 multiplier. And I know the PWM size is going to be 10-bit resolution only. So when the that frequency we changing, the value of PR2 is going to be changes. Okay, at the same time, prescalar will be changes. So based on these two values, crystal frequency and the PWM frequency, I can find what value to be loaded in the PR2 register. If this value changes, definitely the PWM output, what I'm getting, that will be changing here. The next on-chip peripheral, if you talk about the peak, same way as I discussed in the 8051, we have the 5 different types of interrupts in case of 8051. If I mention here, that will be the. Can somebody remember what is that interrupts? Mahite Kundala? 5 interrupts are there different in the 8051. Which are the interrupts? First, int 0, timer 0, int 1, t1, and then we have ti and the ri. So int 0 is called as a external hardware interrupt p3.2 and p3.3. So based on these practicals we have performed. So how to generate the hardware interrupt? So I am connecting the switch button to this pin and I'm sensing that pin output press button is pressed or not. Once button is pressed, I'm taking the action. Okay, hope you understood this. And what is the interrupt? Again, I repeat definition. It is simple software signal. It may be hardware which takes the attention of the controller. And based on its priority mentioned by the vector table, interpreter table, the controller needs to take the action. Means the current program can be suspended, and what is the task is there interrupted, the controller will go to the that subroutine, and that subroutine going to be executed. Once executed, it comes back here. Okay, so these five interrupts were there in the 8051. Similar way, in the peak also we have the different types of interrupts, and just definition as I discussed, same way the interrupt, it may be the software hardware, it can be used in the peak also, or it can be maskable or non-maskable. So in the peak, if you talk specifically 16F877A, it has 15 different sources of the interrupt. Okay, but it doesn't have the interpreter table. If you go to the program memory organization from 00 to the 007H, I think up to that, it is assigned for the various vector addresses of this interrupt. Okay, now all these 15 sources of interrupt can be controlled by using the this incon resistors. And in that we have the flags. If you talk about in 8051, we have the IE and the IP registers for the specifically interrupts. Same way in the peak controller we have the incon, then GI and the PIE. These registers are used for to control the interrupts in the peak controller. So let's go with that. The most similar diagram we have seen also this kind of diagram. I need to enable the external interrupt. This EIF stands for the external interrupt generation. Okay, and once I enable this bit, external bits can be interrupt can be generated, and that interrupt can be or means I cannot generate all the interrupts at a time. Okay, so when the multiple interrupts are generated at a time, based on the priority, it is going to be or, and only one interrupt can be generated, and that is given to the controller, and the controller will take the action based on its priority. In simply, first I mentioned extra hardware interrupt means whenever I am pressing certain push button to be connected at the one of the pins or port pins from the ABCD. That time what happens by enabling these bits also, both signals high, this signal comes high here, and that will be RDI means other interrupts will be by default 000. Okay, so that same signal is coming and I'm giving to the AND gate, and this PE I need to enable, that is called as a peripheral interrupt enable bit. That EA was there in the IE register, 8 number bit. EA is high, in this PE peripheral interrupt is going to be enabled. That time by ordering other interrupts, that particular hardware interrupt will be generated here. And when that it is generated, the CPU goes to the that subroutine, and what is the task is I mentioned here, it will be executed. This is for what? External hardware interrupt. Okay, then we have the peripheral serial performance interrupt here, that is PSP, then AD, ADC, then RC, then timer. These are the TX, they're defined for the timer interrupts, maybe timer 0, timer 1. This is for the serial synchronous serial port, SSP port, is for the communication purpose. The second interrupt is for the just we have seen that CCP model, capture, compare, interrupt. So in that I defined CCP1IF. So whenever the capture register value matches, interrupt occurs. Whenever the compare register value matches, interrupt occurs. Okay. This is for the purpose interrupt only. One is for interrupt signal and one for the enabling bit. Then this second is for the timer 2 generation, then timer 1, and same way CCP1 is there. We have the CCP2 model also, that is for the interrupt. Okay, so these are the various interrupts. Same way as I discussed in the 8051 can be generated. Need to understand it's a control registers first. So I'll bring you to that control register that's called INCON. Okay, that interrupt control registers. So it is again 8-bit size, and based on this value, the various interrupt can be controlled. The first I defined GIE, that is the global interrupt enable bit, like EA. EA was there in the IE register, that always going to be 1. Means I can enable by putting the value high level in this signal. So all bits can be enabled, all the interrupt bits can be set high. This is B. This is 0, all interrupt bits going to be disabled. So the MCQ can be asked like this in the peak microcontroller in the INCON register. The SSBs can be used to enable all the interrupt bits. So you need to understand that is a GIE bit, that is global interrupt enable bit. This is first. Then bit number 6 is for what? Peripheral interrupt bit is there. Peripheral interrupt enable bit. That is PEIE. So IE always stands for the interrupt enable. Okay. So first we character indicates the particular interrupt is there. It is the peripheral interrupt. When I said this is 1, so what is the internal peripherals are there? Like Watchdog Timer, ADC, DAC, capture, compare, serial communication, SSP. So what are the on-chip peripherals are there in the peak controller? That all peripherals can be generated the interrupt, and that interrupts can be enabled by setting the this bit. Okay, so that is called as a peripheral interrupt enable bits. Simple. प्रत्येक बीटला जर हाय असेल तर तो सेट होते. If the value will be 0, that is going to be disabled. Then bit number 5 is for the timer 0. Same way, T0 we have seen when the timer flag register मध्ये value आपण load केली and that values overflows. That time what happens? The timer 0 flag will be set. If this is 1, that timer 0 flag will be set. Otherwise, it will be reset. So I need to use the data, move it in con, and what value be there. If I want to enable this register interrupt, timer 0 interrupt, this is 1, 0, 1, all zeros. In this 1, 0, 1, 0, 0, all these things, it will be A, 1, 0, 1, 0, A, 0. So that value I need to copy into the INCON register. Okay, then the timer 0 flag will be raised. I'll copy and I'll show it here if you're not understanding that. Okay, that is that. To enable all the bits, I need to set this GIE pin 1. If I want to use the peripheral, then I can set 1. Otherwise, it will be 0. Now I want to enable the timer 0 interrupts. So I'm setting 1. All bits will be 0, 0. I don't want other interrupts. So what is value I'm getting? 1, 0, 1, 0 means it's A 0. So I need to move this value. First, I have taken the WF register, so WF A0. Then I'm sending this value move INCON WF. Okay. So what is this value is there? A0. I'm loading into the INCON register. So what is meaning of this? The INCON will control and set the timer 0. And the timer 0 ka we have the timer 0 register. Here M is there. I'm loading with the value F8. And once I started the timer set B TMR0, what happens? The timer starts incrementing the value, and when it reaches to the this value, means what happens? Roll off occurs. Okay, means overflow occurs and the flag will be set, and that flag will be set here. I can check that value. Same way, we have the other bits also for generation of the interrupts. And next bit is INTE. So INTE is for what? external interrupt enable bit. So I need to connect the certain switches or this thing at the any of the port of peak controller. That time I can generate the external interrupt. Same way INT0, INT1 in case of 8051. And these bits RB0, INT1 means what? The port 0 has that pins. If we talk about 8051, port 3, 3.2 and 3.3, that is INT0, INT1 bits was there. In case of peak, RB0, the pin is 0 for the external interrupt bit. If you have the circuit diagram, I'll show it here. Actually, I have that diagram also. This is a peak architecture diagram at 77A. If you see the port B, in that port B, the first pin, P0, port B 0.0, that is 8-bit port is there. This pin used for the interrupt generation. So as I said that port, it is a multifunctional pins are there. Same port, this port also acts as a multifunctional. Okay. So at this pin, I can generate the external interrupt. Means if I connect the switch here, and I'm continuously checking the status of this pin. When the switch is pressed, I need to take the action. Means either port I'm facing some interfacing some motor. Switch press occurs, I can start this motor. And the same program we have seen the edge of fan also. Switch press or not, LED is going to be making on at this particular other ports. Means the external interrupt can be generated by enabling this bit in the intercon register. Then I have the RB IE, that is for the changing, that is port B change interrupt enable bit. So it can act as a port B as well as it can act as the interrupt pin. So by setting this pin can be act as an interrupt pin. If it's 0, that port act just RB pin act as a interrupt. The next is the timer 0 IF flag. That is the timer 0 overflow interrupt flag will be set. This is for enabling. This will be set or not. I can check in this register. Means once I put the value 1010, that will enable the timer 0 interrupt. And if I want to change the interrupt timer 0 interrupt occurred or not, so by checking this pin bit number 2, I can check the status of this bit is high, then timer 0 interrupt is going to be occurred. If this bit is 0, the timer 0 interrupt is disabled. It is not occurred, I can say, simple meaning. The next bit is INTF, that will say that what? The external interrupt flag is set or not. Means once I enable external interrupt, and when I'm pushing this, connecting the switch at RB INT pin, port B pin, first pin, and switch is pressed means what? At this point, I can say the flag is going to be set for the external hardware interrupt. And the last is for RBIF, that for the port B. This is to control the various interrupt. This intercon is going to be used. Similar way, I have the IE register, that is IP. Like in the 8051, we have the IE and the IP. Similar way, I have here also IE register to set or reset the interrupts. The first bit, if you talk about the on-chip peripherals, that is the parallel slave port interrupt enabling bit is there. Okay, so once I set this, we have the port pin and it's a peak controller. So by setting this bit high, I can set the parallel slave port read write enable interrupt. Okay, then second bit is for ADIE, that is for the analog to digital converter interrupt enable. So simply when I'm putting giving analog signal to the peak controller at the AD, one of the channel of the ADC, and once conversion overs, the ADC will set the flag, that is ADIE. If this bit is 1, the flag ADCA analog digital converter flag will be set. If it is 0, it will be reset. Then RCIE, that is for the USART serial interrupt enable. Means whenever other peripheral sending the data to the peak controller, once this data is received, that time this RCIE bit will be set, means the receive interrupt will be generated. If this bit is 0, no receive interrupt is generated. Like if you can say that in the SBUF register, when the data will be received at the 8051, the RI flag will be set. And when I'm transmitting, TI flag will be set. So to receive the data in the peak controller, the RCIE flag will be set or reset. Similar way, TXIE for the transmission purpose. Means just nomenclatures are changed here. This will be RI, this will be TI flag. Similar way in the 8051. Then SSPIE, that is synchronous serial port interrupt is there. So all these are the on-chip peripherals, and for that I can generate the interrupt or not. Meaning is that what is the data? The synchronous serial port will send the data synchronously by depends upon the clock signal given, and the port can be varied. And whenever data is sending, this interrupt can be generated. Next bit is CCP1IE, just we discussed previously also. That is the capture compare PWM generation. So when I'm capturing the data or I'm comparing the data, once match occurs, the flag will be set. That is for that. And the last two is bits for timer 1, the timer 2 flag generation. So this is, so by using this two registers, INTCON and the PI1, PIE1, I can generate different interrupts in the peak microcontroller. And all the interrupts will be generated only one at a time based on its priority. Which simply क्या है, तो मला timer 1 interrupt जर raise करा असेल, so I need to configure this INTCON registers, and the timer 1, it is not in the timer 1. We have the timer 1 here. So this timer 1 flag will be I need to configure to set high. Then only I can generate the timer 1 interrupt. Okay. So this is for the interrupt generation in the peak microcontroller. Next module we have on chip device that is called as the Watchdog Timer. So this is a very additional interesting timer which will be helpful in the peak microcontroller whenever the software failure occurs and our CPU means the peak controller goes in the sleep mode. That sleep mode, to wake up from that sleep mode, I need to use the another device, and that is called as a Watchdog Timer. आता ह्या वॉचडॉग टायमरचं नाव तर आपल्या म्हणजे यू अंडरस्टूड माइट बी कशावर दिलेलं आहे. ओके, सो आपण म्हणतो आपल्या घरी काय असते, एक डॉग असते, आणि त्या डॉगचं काय असते, कंटिन्युअसली मॉनिटर करायचं रात्रीच्या तरी कोण आले का नाहीये. ओके, सो दिस इज माय पीक कंट्रोलर, I can say microcontroller, and in that device only I have the watchdog timer. Okay, this is the watchdog timer. So one of the output of that internal is connected, and this output TO pin timer out is given to the master clear register reset circuit of the peak microcontroller. Means what happens whenever the microcontroller CPU is goes in the sleep mode and this performing abnormal operation, म्हणजे काय तर task चालू आहे नाही, it is starting going in the sleep mode. That time this watchdog timer will be reset it this controller and start from the it's what is the address mentioned, from that it will be start its operation. Means what? The function of this watchdog timer to keep continuously monitoring on the peak controller to see that it's an abnormal operation going on. If it is going on, it will reset this controller by a T-out pin of the 8051. Okay, so that is meaning of the watchdog timer. And this watchdog timer has separate registers, that is oscillator. It does not operate on the what is crystal connecting externally, that's 70 megahertz. It has a separate free running oscillator which is forming the RC components, and based on this value it will generate the one clock for the timer operation. Okay, so we'll see its diagram. Watchdog timer, it has various internal resistors to monitor the peak controller. We'll see that. Okay, how it works, that is important. So watchdog timer is loaded with the timeout. As I said, the T out value. So this T out, just when I have the call. Okay. So how timer works? So what is the value to be loaded in the time? As we know, the timer is what? We need to upload the count value in that. And once count value overs, it takes action. So every time I need to load the timing out value in the watchdog timer. And once it started, its value going to be starts incrementing and its value going to that. In that time period, the watchdog timer, if the certain things goes abnormal, it will reset the controller. If not, it will take the same value automatically. It reloads the same value automatically. Okay. Second step, the watchdog timer counts the independent as a system clock. Just I mentioned, it is independent of the what is the clock I'm using crystal oscillator. Watchdog timer cleared through the software each time before timeout period occurs. म्हणजे what is the count value I'm loading before overflows that value, I can reset the watchdog timer value by through the software instructions. And what is that? Whenever the software failed to clear watchdog timer before it's a timeout, watchdog timer resets the system. म्हणजे आपल्याला सॉफ्टवेअर थ्रू द व्हॅल्यू स्टोर्ड इन द watchdog timer जर क्लिअर करता आली नाही, that time this watchdog timer, as I mentioned here, it clears the peak controller automatically. That is the funda of the watchdog timer. थोडक्यात लक्षात ठेवा, the task of this watchdog timer to keep continuous track on the peak controller. आणि पीक कंट्रोल जर आपल्याला सॉफ्टवेअर फेल्युअर ऑकर होत असेल, इट रिसेट्स द पीक मायक्रोफोन ऑटोमॅटिकली. दॅट इज फंड ऑफ दॅट. म्हणजे ह्याला नॉर्मल म्हणतो की आपण जेव्हा पीसी वगैरे वापरतो, इट हँग्स आउट, म्हणजे त्याला कंट्रोल करता येत नाही आपल्याला. बट इन केस ऑफ पीक और एम्बेडेड प्रोसेसर, वी हॅव ॲडिशनल डिव्हाइस, ते त्याला स्वतः इंटरनली मॉनिटर करतो. म्हणजे जर आपला पीसी हँग होत असेल ऑटोमॅटिकली कंट्रोलर, इट रिसेट्स दॅट सिस्टीम ऑटोमॅटिकली आणि इट गोइंग टू बी परफॉर्म द नॉर्मल ऑपरेशन. That is fundamental principle of the watchdog timer. जसं मी एक्झाम्पल सांगितलं, आपल्या घरी एक डॉग असते, त्याचं टास्क आहे कंटिन्युअस मॉनिटर करायचं घरी कोण येते का नाहीये. म्हणजे अननोन जर गोष्ट कोण आलं, ती स्टार्ट्स बार्किंग. ओके. अँड इफ नोन पर्सन्स आर देअर, नो इश्यू इन दॅट. सेम वे whenever abnormal operation is going on, it resets the controller. That is principle of the watchdog timer. See, it's a diagram is here it mentioned. How to load all this value based on the PSA condition in the timer zero operation also आपण बघितले आहे की PSA म्हणजे काय, प्रीस्केलर असाइनमेंट. हे जर बिट 0 असेल तर काय होत आहे, इट टेक्स द टाइमर zero operation, all this thing. If this PSA bit is 1, that time I'm assigning the watchdog timer operation. Means मगचं फंक्शन काय 2:1 आहे. तर 0 असेल तर it takes the clock from the timer 0. If 1 is there, it takes the output from the timer. Means PSA prescaler assignment will decide that either I can use the timer as the watchdog timer or the simple timer operation, time zero operation, based on the these two bits. And that value output is given to the postscalar multiplication. In the postscalar, 1:2, 1:2, it is 8-bit only, 1:1, 1:2, 4, and 8. That things can be multiplied. Okay, and how to multiply based on the values stored in the that register PS0, PS2. Means 3 bits are there, 00 to the 111. मग त्यावर आपण सिलेक्ट करू शकतो की कुठल्या व्हॅल्यू मला मल्टिप्लाय करायचं आहे. ओके, 8:1 mux means it has 8 values. Okay, and out of that, this output is given to the again mux number 5. In that, if PSA bit is 1, that time I can take the multiplication of the postscalar and the prescalar values. If it is 1, if the thing is 0, I can provide the watchdog timer count value without the prescalar and the postscalar values. Means again depends upon the PSA at the mux 2 5 output. If it is 1, I can generate the timeout value with the prescalar multiplication. If it is 0, without prescalar, means directly output of the watchdog timer is given here. Without, it will not take the this processing here. Okay, means multiplication of the prescalar and the postscalar. That same operation is mentioned here. Mux 2 select the either timer or the watchdog timer. 0 select timer 0. 1 असेल तर mux 2. Mux 3 काय 8-bit prescalar multiplication select करता येते. आणि mux 5 मध्ये एक तर ते 0 असेल तर विदाउट prescalar व्हॅल्यू सिलेक्शन आणि 1 असेल तर विथ prescalar. हे डायग्राम मध्ये बघितलं आपण. 1 असेल तर विथ prescalar, 0 असेल तर विदाउट. म्हणजे जी क्लॉक सिग्नल जनरेट केलेला आहे तोच मला आउटपुट भेटेल येतं जर जी व्हॅल्यू 0 असेल तर पीएससीची ते इफ 1 असेल तर जी व्हॅल्यू जनरेट केलेली आहे त्या व्हॅल्यूला मी मल्टिप्लाय करू शकतो 1 ने 2 ने 3 ने 8 ने दॅट इज मिनिंग ऑफ प्रीस्केलर मल्टिप्लिकेशन. So up to this point we'll stop here. Remaining point is the ADC and we have remaining this chapter ADC I think and IO ports. Then we'll finish this chapter also. Okay, we'll stop it here. Thank you. Let me take attendance and then you can leave out. One, two, three, 4, 5, 6, 7. 7 is not there. Absent. 8, 9, 10, 11, 12, 13, 14, 15. 15 is not there. Aditi Patil. I know the names of the students who is remaining frequently absent. 17, 18, 19, 2021. Who is 21? 2, 2, 2, 3, 2, 4, 2, 5, 2, 6. 2, 6 is also not there. 2, 7, 2, 8, 2, 9, 30, 31. 31, 32 is not there. 33, 4, 5. Katare Azale Baba. 5, 6, 36 is not there. 7, 8, 9, 38.
36 present.
आहे का? ओके खरात ना ते नाव चेंज करी तुझं 30 नाहीये 39 आहे 40 नाहीये 41 आहे 42 नाही आहे 3 4 5 6 7 8 8 9 is not there 50 51 is there. Okay, thank you. You can go for your next lecture lunch.